Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at logarithmic graphs. So we know that logarithms are the inverse of exponential graphs. We've already seen a graph like this. This is the exponential graph y equals 2 to the power of x. Well, this graph in green is the graph of y equals log base 2 of x. They are inverses of each other. So geometrically, this means they're actually reflections of each other about the line y equals x. This is like the mirror line. And they have several things that are sort of opposites of each other. For example, you might see y equals 2x has a y-intercept of 1, so the log graph has an x-intercept of 1. You might see that the exponential graph has a horizontal asymptote, whereas the logarithmic graph has a vertical asymptote. The exponential graph is increasing at an increasing rate, so it's getting big really quickly, whereas the log graph is increasing at a decreasing rate. It gets big very slowly. All right, let's now have a look at starting with an equation and turning it into a graph. So we need to be able to graph functions of the form y equals log base a of x plus b plus c. So the first thing you should do is graph the asymptote. There will always be a vertical asymptote, and it's always the negative of this value in the bracket. So the vertical asymptote here is x equals -2. So I'm going to draw the vertical asymptote. Now, why is this the asymptote? Remember, you can't have log base 3 of 0 because you can't raise 3 to any power to get an answer of 0. So what's in the brackets can't equal 0. That's why x can't equal -2. X equals -2 would make this bracket equal 0, which we can't have. That's why the graph can never hit along this line where x equals -2. So let's look at the general shape of the graph. So when I say a, I'm talking about this value here. So if a is greater than 1, it's going to go like this. And if a is less than 1, it's got to be greater than 0. But if it's greater than 0, less than 1, it's going to come down like this. So really all we need then are a couple of points to help us see where it goes. So let's just sub in a couple of points. Now, there will always be an x-intercept of a logarithmic graph. There won't always be a y-intercept, there'll always be an x-intercept. So let's just find the x-intercept for one of these points. So the x-intercept always occurs when y equals 0. So I'll just change y to 0. So all I've done is take this equation, y has been changed to 0. Now I'm going to add 1 to both sides. Now I've got a log base 3 of something, so the way I undo log base 3 is raising 3 to the power of each side. So 3 to the power of 1 is 3. I get 3 equals x plus 2. Subtract 2, x equals 1. The x-intercept is x equals 1. So I will put a dot here. Now let's just substitute some other values of x that will give me an idea of where this is. So for example, I can substitute x equals -1 in here because -1 plus 2 is +1, which is okay. Log 3 of 1 minus 1 is -1. So the graph will go through this point, -1, 1. You're probably starting to see how it looks. You can just keep adding points until you see exactly what it's going to look like. So for example, when x equals 7, I get log 3 of 9, which is 2, minus 1, which is 1. So it will go through this point here, 7, 1. So we know that by definition of the asymptote, it'll get closer and closer to, but never touch the asymptote. It's going to come up and go through these points. This is what the graph will look like. All right, let's now look at an example where you're given the graph and you have to find the equation. So we're going to find the equation of this graph here, being told its equations of the form log base a of x plus b plus c. So really all we need to do is find the values of a, b, and c. Now, b can be obtained first from the asymptote. It's easy to find. See, the asymptote occurs when x equals 1. But the asymptote of any log graph occurs when this thing here equals 0. That gives us the asymptote because we can't have log base a of 0. So x plus b equals 0. We were told the asymptote occurs at x equals 1. That was given to us in the graph. So that, of course, means b is -1. So we found B. Let's update our equation. It's going to be log base A of x minus 1 plus C. Now we just need to find A and C. So we can use a similar trick to find C that we used when we were finding the equation of an exponential graph. So for C, what you can do is start at the asymptote, go 1 to the right, and whatever the y value is at that point, that is the value of C, because that tells you how far it's been moved up. So in this case, the y value when we moved 1 across was 2. So I'm going to rub out C and replace it with positive 2. Okay, this just leaves us A to find. So the way we find A is the same way we found A many times in many different graphs. We're going to substitute a point for X and Y to find A. So we're not going to use the point we just used, because this point we've already kind of got all the information out of it. We're going to use another point whose coordinates are clearly visible, and that's this point 5, 3. So what I'm going to do is I'm going to substitute Y for 3 and X for 5. So I get log base A of 5 minus 1 is 4 plus 2. Subtracting 2 from both sides, I get 1 equals log base A of 4. Of course, by definition of logs, that means A to the power of 1 is 4. Of course, A equals 4. So the equation that I had up here, now I can just rub out A and replace it with 4. This is the equation I would start with to end up with a graph like this. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.